A couple of news items to talk about today. As you can tell, I had surgery yesterday on my mouth. I had to have another round of surgery. I even got a third after the semester is over. So go a little easy on me. They had to give me a whole bunch of drugs because it was like a lot more, it wasn't as bad as a root canal, but it was almost as bad. And so that's why when my cat did something bad this morning and I was chasing after her, I slipped and heard a pop in my hip. I know you're used to hearing a pop in your ankle or your knee, but it's in my hip. And I think it's getting better, so I got a sprained hip, so I'm not going to jump or do much. Actually, I'd rather be in a wheelchair, but anyway, so I may not move around a lot, but just do it kind of easy on me today, all right? I'm really having incredible pain. So, okay, class, come on guys, come on. All right, so class business. So this is the last Friday of extra stuff, and instead of the double lecture, I'm not going to do a double lecture because I don't have much to talk about in terms of, we're doing more, guys, right there, all right. In terms of phase diagrams, we're doing more phase diagrams, we'll probably spill into Monday, and it's just so easy that I kind of just don't like it because it's just so damn easy. Although it'll make an easy third test for you, and maybe I'll have a question on the final as well. I'm not inclined to that. What else can I tell you? Okay, so in the next hour, because I don't really see a need to do a double lecture, because I mean, like I say, I've really covered everything that you traditionally cover in PChem 1, with after today and maybe Monday. I mean, we're done, right? As stated before, we'll do some topology to finish up the semester. And this extra hour, we're going to do 346 things, which is going to be differential equations. Because differential equations are half of 346, because quantum mechanics is the math of quantum mechanics is the math of differential equations. So I'm going to introduce you to differential equations. You actually already been doing it, but you didn't realize it. And show you a couple of examples that may or may not be useful in 346, and then we'll conclude with second order differentials, with differential equation solving, which is quantum mechanics. And I'll explain why that is. So I spent definitely a lot more time on this lecture than the others. I know that I didn't feel like I did such a good job with the last 2 extra hour Fridays on 346, but I think hopefully I'll stuck it on this one. And I have the whole hour taken up, 6 pages of notes. So Again, that should really help you with 346. And even if you don't remember this stuff, you've seen it before. Somewhere in the back of your head, subconsciously, when you see it again, if you don't remember what I talked about today, it is in the back of your head somewhere. And sometimes, constant repetition is actually a good way to learn things. So I think this is really going to help you with 346. And I'm not worried anyway. Everyone does well with 346. It's just incredible because sometimes, I swear to God, you write an equation that goes all the way across the board and you have to deal with that. So anyway, that'll be the next hour. In terms of the fake problem set 11, I got nothing. I mean, I got no questions to write even because these phase diagrams are just so easy that I'm going to give you every example I could have possibly asked. So that's kind of a screw over, I guess. I mean, it's, I'm not going to write a problem set because it's too easy, but I'll give you this. Today's material is pretty interesting, and so whatever question is on the third test will come from today. Watch the video. I'll make sure I'll have the video up as soon as I get back, and I'm not bad about that. I'll have this up today. And just watch that over again. That answers a question. Maybe a life, the universe, when a life, the universe, and everything question. And don't hold me to that, but I'm leaning towards that way. So watch the video if you got one of those nailed. That's a 10-point question. Not bad, right? Any of you have questions? We're okay? Yeah?
Can you briefly go over again the chemical potential, or temperature versus chemical potential graphs?
How about the next hour?
Sure.
All right, because a little bit way back.
Okay.
Yeah, I'll do that, and then I can talk about differential equation. You'll be here?
Yeah.
Yeah, okay. So, yeah, we'll do that. Any other questions? We're okay? All right, yeah, so let's just get back into it. So we have this pressure versus composition, phase diagrams. And I'll just remind you what we did last time. I'm not, we'll call this species A, observer 1. So there's a B present. I'm not drawing B, it doesn't matter. B is 1 minus A. And, well, let me just review before I tell you what I'm thinking about this material. Remember that this was the Rayleigh's law, pressure versus composition of the liquid. And of course, the partial pressure better be B. So this is something with A having a higher pure partial pressure. Remember, that's what the star means, pure partial pressure. And remember that Rayleigh's law predicts a line, so these are ideal. But when we did the same thing for the vapor phase, we saw that unless the partial pressures were equal, which is really never going to happen, you could have this line bend below, or it could bend above. It could bend above, no, I'm sorry, no, that's not, it can't bend above, I'm an idiot. Okay, so questions like this, all right, so I am going to ask a question like this, except it'll be based on today's material, but what you got to get used to is I'm not going to identify what's what. All right, I'm going to tell you this is a liquid vapor diagram. I'm only going to give that much. Now you have to figure out the rest. So you got to walk yourself through it. Don't memorize this stuff, right? Forget trying to memorize this stuff. Focus on electrochem and all that jazz. Right? And again, once they build the high pressure, that means that at high pressure I got to have the liquid. And that means that this is the vapor. Am I doing that right?
Yes.
Yeah, I'm doing that right. So just a little out of it. And that makes the middle the liquid plus vapor. And we talked about this. Here, I'll draw a point. Sorry, I put these in bad, but don't worry about redrawing this. I'll draw a point. You draw 2 lines left and right. You drop down. And now you just got to identify that these are compositions. Compositions? I see you. Anyway, in the back of my head. All right, so now the only hard part is I'm going to have tick marks. And I'll have these, I'll line them up with a ruler, and I'm going to say, hey, give me the composition of the liquid and the vapor. And so you recognize that this is the liquid and that this is the vapor. And that's it. So this would be like 0.4, and that looks like 0.7. And again, I'll make sure the tick marks are very clear. And then I'll also ask, what do I have more, liquid or vapor? Liquid. You're saying that because I dramatically turned around, by the way. Yeah, lever rule. Remember this kind of, guys, this is easy. If you don't remember the little formula for the lever rule, NA over NB is IB over IA. Look at last video. So, it's easy. The point is closest to what? Liquid. Right, the liquid line. So there you go. There's more liquid. It's just that easy. Just remember that. That's not hard. Okay, again, this is a review of what we did last time. What we're going to do is instead of pressure, we're going to do temperature. And this is more interesting, which is why I want to actually put this stuff on the test and I'm just not quite as interested in this, especially with Rayleigh's law, which I don't like. So let's forget pressure and let's do temperature. And we're going to do vapor, liquid, sorry. It doesn't work well today. And I'm not going to solve a bunch of equations because, like, remember this one, we solved a bunch of equations that gave us all these curves. And I don't know how to do that for temperature. I just know what the result is. And I'm just going to, again, this could tip any which way. They tend to look like this. And then, again, this is going to be, remember, it's a double axis, and one of these belongs to one axis and one of these belong to another axis, whether it be the liquid composition or the vapor composition. Also, sorry. Of course, I want to make sure that you know that it's species A goes from 0 to 1. And so what you want to recognize here is that this is the boil of A, and then this is the boiling point of B. Certainly a question I could ask on a test, put a little tick mark and say, hey, what exactly does that temperature mean? And you say, well, it's the boiling point of species A. Okay, now, I have told you this is a liquid vapor, all right, that's all the information you get. High temperature, low temperature. Okay, this phase? Liquid. Yeah, of course it's a liquid. And this is the vapor, of course, and then that makes it the liquid plus vapor phase. And remember, all this, these are ideal solutions. We're actually will do non-ideal solutions in a moment. And that's kind of cool, really interesting. Because, you know, remember how absolute these things are? Like even when we did the one component phase diagram, like on question 1 of the last homework, we had to find out what was wrong. This says that there's no vapor present. I understand that I'm below the boiling point, so I've mostly got liquid, but I know that if I wait long enough, my water eventually evaporates. So this isn't really true. So that's a problem with ideal solutions. Okay, now you gotta learn how to read it, which is quite easy. Just draw an X there. And now you drop down. Again, if this is on the test, the tick marks will be perfect. You'll be blind not to see what they are. Even if you're a little off, it's okay. You can count off. This looks like 0.9, that looks like 0.6. The question is, this is chi or y? Chi, it's chi A. Right, because it touches the liquid line. Remember, y's are for gases. I'm not going to ask you to remember whether it's chi or y. I'm just going to say, tell me the liquid, tell me the vapor composition. I'm not going to say what's chi and what's y. Right, that's kind of stupid. All right, now here's the thing that's actually really awesome about these things, is that, and I'm going to redraw it, because there's actually this really, really very interesting thing is hiding in here. And chi A or y A, you figure it out, 0 to 1, and I'm just drawing it again. I just don't want to write over what I just did. Slopes a little bit more, but anyway. Okay, again, this is the vapor, this is the liquid. I'm drawing it this way to get these things out of my way. I'm going to get a different starting point. And so there's my vapor, and there's my liquid composition. So my vapor is rich in A, and if the vapor is effervescing off and taking A with it, well then the liquid's going to get richer in B. So this makes sense. Now here's a magical thing. What if I could take the vapor and I cool it? Get it back to a liquid. Right, let me draw a little like arrow so you see what the heck I'm doing. Okay, now I've got a liquid. Now composition hasn't changed. Obviously, why would that wouldn't make sense? But now I'm going to evaporate it again. And my vapor, again, for some reason, I guess has a higher partial pressure. I mean, that makes sense. So it comes off easier with a little heat. And then what can I do? Cool it again. Okay, now I've lost some material at this point, especially after I heat it up and cool it down and heat it up. And yada, yada, yada. Making the vapor almost pure A. Ever heard of that before? Distillation. This is the process of distillation. This is how it works. So, yeah, so there you go. That's just kind of neat. And the way I like to represent this is to show what's basically happening is you're moving this way in the gas. That's the one little arrow. And this guy is the liquid. Good. Okay. So, the more and more you can do this, the higher the purity of A vapor comes out, although of course it looks like in these condensation evaporations, of course I have to leave some liquid behind, liquid rich in B, to create a vapor high in A. So by the time I go from here to here, I probably don't have a lot of vapor, but that's okay because it's pure, and I'll just keep drawing it off. And I can do that and do that until the liquid is pure B. And then there's no more A left to collect anyway. As long as you don't turn off the heat, you won't screw that up. And the process by which that works is like this. Let's see if I can draw a little bit better. And you don't have to draw this, by the way. We have a little column, and the top is something that will siphon this out. what is wrong? I can't draw straight lines over the drugs again. I had to take 6 times the painkillers last time because the procedure was just that much worse, so it threw me for a loop. Okay, well, you know this is a distillation column, and you know distillation column has dimples all along the side. And when you're doing a distillation, you can see the liquid droplets form on these things, and of course you know that they're effervescing. And doing this further, and you get progressively smaller drops, but that's okay because the vapor is all A. And of course, don't forget there's a heating source underneath it. And so the heat, you know, there's hopefully you did this under nitrogen gas in case these things are flammable. So as the liquid forms here, this heat will cause the nitrogen to heat up, and of course hot air rises, and that's why those will continue to evaporate. But they do get more and more pure for exactly this reason. So there you go, physical chemistry explanation for distillation. Now here's the problem, and unfortunately it's a common problem, and that is an azeotrope. Okay, azeotropes are liquids that misbehave. This is equal to non-ideal. Okay, now remember, truly ideal liquids are like O-xylene and M-xylene, right? Xylene is toluene with an extra methyl group. Those are very ideal because molecularly they're almost identical. Hexane, heptane, I guess, that would work. Almost identical. You're not really ever going to want to distill something like that. Actually, sometimes if you're trying to purify long-chain fatty acids, if any of you ever seen, God, there was a movie with Nick Nolte and Susan Sarandon many years ago, Lorenzo's Oil. It's an old one. I saw it when I was your age, so that was 5 years ago. And, Lorenzo's Oil was about this kid who had this demyelination syndrome, which is basically like Parkinson's or like Parkinson's essentially, except it's really bad because it hits young boys. And it turns out they figured out that only one very heavy long-chain alkyl acid would actually cure it. And the kid actually just passed away, but a lot of lives were saved by this. So, anyway, you should see that movie. It's actually really good, but it has some chemistry in it. But for the most part, you're going to be distilling things like ethanol and water every day, hopefully. And ethanol, water are azeotropes, and most things are going to be azeotropes. Most things are non-ideal. Okay, so when you have an azeotrope, in terms of distillation, you got yourself a major problem. And let me remind myself what I'm doing. Okay, so those, sorry. Okay, I've got, I'll keep thinking in terms of A, not that that matters. Okay, what these guys are going to do is something like this. And remember, these are very, very interesting. They work like that. Okay, now again, vapor, liquid? Liquid. And don't fall asleep. Vapor and liquid vapor. Okay, so this is probably the most interesting phase diagram I can probably offer up because it does a lot of really cool things. For one, all right, non-ideal. Remember that means that there's like an enthalpy of mixing. It means that my interaction, B's interaction with A is not the same as B interactions with B. They could be better, they could be worse. Like HCl loves water. HCl loves water more than it loves HCl. That's definitely true. So in some liquids, they just don't really like to mix like that. Remember that triethylene water thing I had the other day, about a month ago? Okay, now I can tell you in terms of, is the AB interaction stronger than the AA or the BB, or is it weaker? That's my question to you. I can tell from this diagram which one it is. Stronger, AB, is it stronger than AA or BB, or is it weaker? Okay, folks, tell me what you think. Stronger or weaker? Now, here, let me point this out. All right, here's the hint. Oil B, the temperature. Okay. Now, again, stronger interactions, meaning they don't like to be apart, or weaker interactions, which is like, get the hell away from me. Stronger. Why?
It's increase in boiling point.
I just heard squirrels. Sorry, it doesn't work when everyone speaks at once. The temperature of boiling has gotten higher. So at this composition, that's like the perfect buddy-buddy composition. They like each other so much they don't want to be apart, which will happen up here. Right? They don't interact in the vapor phase if they're perfect, but the temperature got raised. They're holding on to each other harder than if they weren't separate. Right? The temperature got raised. Okay, so I can tell that. Now, let's look at the consequence when it comes to distillation. Let's put myself here. Okay, now, I won't bother asking the audience what's what, because hopefully you figured this out. This is actually pretty easy. And then here this is the liquid, but now, of course, I'm going to do my thing. And note that, and here, I'll just erase that, so it doesn't get confusing. Sorry, I just screwed up your notes. So while you're pouring off the vapor, the liquid is getting to this point. So again, this is the liquid, and this is the vapor. I'll try to draw fancy here, we're not good at this apparently. And here's a little arrow to remind you where it's going. Okay, so there's a lot going on in here. Actually, I know it looks simple, there's a lot going on. All right, for one, I am able, with a really long column with lots of dimples, I can get the vapor in pure A form. That's great. So I can get the vapor in pure A form. Now, as I do so, as I draw it off, the original composition of the liquid, is slowly moving to this point here. Right, so I'm drawing A off because the vapor is pure. I can make the vapor pure in A. So that means that the liquid is losing A until it gets to that point. Now, the damnedest thing happens at this point. Now, remember that the slope, this is at an apex. I didn't draw it too well, but this is at an apex. And you want to think of the first change in composition as being like a partial of the vapor, or the partial of the mole fraction of the liquid phase. The problem is that doesn't technically get you anywhere. The slope is zero. So going forward or backward doesn't actually do anything because the partials are fairly small and it's... We're names doing this, right? I want to see if it just goes back up. So, okay, now because again, the first incremental change in composition is a partial, and I'm sitting actually at the flat line. Okay, I'm actually sitting on a flat line. Once you get to this top point, the vapor is composed. So I can turn up the heat and still get it to boil. Right? I can always raise the temperature, but the vapor, because it's again sitting at this apex with the slope of 0, the vapor will be at this composition. So all I can do is boil the solvent out of the pot, which is useless. Question?
I was going to say, when you do the arrows for liquid and vapor, that's not saying that that's the vapor line, that's the
Wait.
liquid line.
Did I do that wrong?
Very good.
No, you were right. I got it right. I don't really care about this, but I'm just curious how it's happening. Sorry, now your question again was, I don't think I answered it.
So when you said that the liquid line is up there with the direction going left.
Right, now this is the vapor line, but this is where the liquid is going.
Right.
Yeah, that's a little confusing, especially with the last one, right?
Okay, no, I was making sure that that's what it was.
Yeah. I know that's a little confusing. I'm just trying to show you where the vapor movement is going. Okay, so now here's blue lights. I'm sorry, Dave, I can't do that. Oh my God, actually made that reference. I'm very happy by with me. Shells thing's awesome. Okay, so with an azeotrope derivative, what's good is you can get pure A, but you're not going to get a lot out of it. And again, you're going to be left behind with a liquid that looks like 1/3 A, 2/3 B. And again, I can still boil this liquid, but the vapor will have exactly that one, looks like 1/3, 2/3 composition. I cannot separate them anymore. So I can tell you that since I'm I'm a physical chemist who does a lot of synthesis, and this is very common, take ethanol water. Water will, you can't get rid of water to the tune of about 5%. So distill all you want, go out and brew your barley, malt it. I used to make beer, malt it and distill it. And what you will find is that the vapors will always be at 5% water. So what can you do? What can you do with this liquid? You want to get rid of A, but you came to a stopping point. As the synthetic chemist in me knows what you do. You get something to react with A. Let's say it's water. What you would do is, and this was ethanol, what I would do is I would throw in a little magnesium. You don't have to write this down, I'm just telling you. I throw in a little magnesium and a little iodine. And what that does is it makes a Grignard out of the, remember that organic chemistry? It makes a Grignard reagent. That is actually massively reactive with water. The byproducts are more ethanol, which is what you were trying to collect anyway, and magnesium oxide. Magnesium oxide will float to the bottom. It's a solid. The magnesium, the iodine are solids. They're going to float to the bottom, and they're going to stay there. And then when you do your distillation, those impurities you added stay there. And then you distill over pure ethanol. That's how you actually do it. So, all right, anyway, just so that's kind of deep. As a physical chemist, you never learn that kind of stuff, but it's, synthetic chemists did PhDs for a reason. And when I was in physical chemistry in grad school, we sometimes made fun of them. We were just like, oh, these guys just work all the time. They do work very hard. And I never really appreciated what they do until I had to do it too. Okay, let's draw the other type of azeotrope. This is the bad azeotrope. This azeotrope, when you run into this one, you got problems. Bad problems with this guy. And again, I won't bother with, this is obviously the liquid, this is obviously the vapor. And I'll pick a point and try to figure out what happens when I do this distillation. Looks like, okay, so that will be my liquid line. This will be my vapor line. So I hit that marks up spot. Okay, so this is the, sorry, I've been inconsistent with calling something a vapor or a gas. But they're the same thing, right? You know that. So, okay, as I'm drawing off, this is where the liquid is going. Okay, so bad situation. Normally when we distill something, we're trying to get the vapor. The vapor starts out, looks like it's rich in A. As it goes up the column, it becomes more rich in B. Looks like it's about maybe 40% A and 60% B. The problem is that you're never going to do better. And I believe this is an ethanol water situation where this is actually typically 5% water. But anyway, little arrows, OCD arrows, that's what I call them. So anyway, so you can't collect a pure vapor. And that's not, most distillation apparatuses are designed to capture the vapor. So that already is kind of starting to be a little sucky. Okay, but the liquid, as I draw A into the vapor phase, B, sorry, as I drop B into the vapor phase, this is becoming rich in B and less in A. So drawing B into the vapor phase, that makes the liquid pure. Okay, so no matter what azeotrope, you can get something pure. You can either get the vapor pure or the liquid pure. But the big cost is, so you still can separate them. The big cost is that, look at how you're forcing this to happen. You're taking out a lot of vapor. You're taking out a lot of vapor that's slightly more rich in B. And you have to keep doing that for a very long time until you get your pure A. And the way I've drawn this, it looks to me like it's 50-50. So in other words, you start with a liter of B and you add some A, whatever. To get that B pure, to get all that A out, it looks like I'm going to lose half of it to the vapor phase. Well, yeah, okay, it's great. I got pure B, but I've lost most of it because I had to suck it out with a lot of A. And so that blows, but it does work, but it blows. And again, if you actually were trying to get pure A, you're going to have to do it chemically, which is actually more common. So, anyway. So you can imagine I could throw one of these at you and ask you about whether it has strong interactions, weak interactions, which way does the azeotrope go, what are these points, that's one point E, 1 point A, Where's the vapor, where's the liquid, where's the vapor liquid? Wow, that's like a 10-point question. Professor's not calm anyway. So there's a gazillion of these. I don't think I'll get through them all, so this may spill over until Monday, when we'll maybe just finish up some of these, and then we'll introduce topology, group theory, that some of you have had, and then I'll make it clear on Wednesday what's on the test. I'll write it this weekend, so it'll be pretty easy this weekend. Let's do liquid. Sorry for the abbreviations. Now, ideally liquids, ideally all liquids mix. So this is automatically non-ideal. So the phase diagram of a liquid-liquid mixture is a blank sheet of paper. It's nothing but a mixed liquid. Okay, if it's not ideal, then you know that those liquids may be immiscible. Now, here's the truth about immiscibility, is that there's no such thing. Think about, think about how liquids mix. And let's do this. So I know that a negative change, and this will be total entropy, because this will define everything. I'm not quite sure how the outside entropy can be very effective, but whatever. So I know that I want a positive change in entropy, but I also know the liquids don't mix. Now these kind of have to be symmetric. So let me try to make sure I do it right. There we go. Okay. Now what's going to happen is in this liquid mixture, again, for the most part, any composition, I have to, this is chi A and B. Those are my two. Sorry, what am I doing? No. I'm beginning to, never mind. Framing doesn't work. Okay, what I'm going to have is, the two liquid phases, phase one, will have very little A, and then this will be chi A of phase two. So now, the truth is about any liquids that don't mix, that's not true. All liquids mix. It's just a matter of how far these little slight rises in total entropy are. So something like ether, I believe, is saturated to about 10% with water, which is really kind of gigantic, and that's a problem when you use ether as a solvent. Hexane, very little water, but there's some. There is a tiny bit of water, and a real synthetic chemist, like myself, if I'm doing a systemic reaction with hexane, I actually have to kill off the water. Any guess how I do it? Distillation? Any ideas? Take a piece of sodium, throw it in, stir it overnight. And you actually usually have to reflux it too. So the sodium obviously reacts with water, so when I distill the hexane, the sodium stays at the bottom, and the sodium that reacts forms sodium hydroxide also stays at the bottom. I pull it over until I collect all the hexane. Here's a problem, and just FYI, because I do a lot of synthesis. That type of distillation is now considered, you don't do it anymore, because it's dangerous. Here's what happened, especially for THF. THF is an epoxide former, and I believe if you purify THF, I think that might be done with sodium as well. You have to make certain that you use the right thing. If you try to, I'm gonna purify, I'm gonna get rid of the water of this solid, and you throw in sodium, you might have just made a bomb. If you do it with hexane, you're fine. So there's always a dryer for every different type of solvent. And just look at Google. But if you get it wrong, you can blow up. THF is very dangerous. I've done this before in very small quantities. When you're purifying THF, you add the chemical reactor to get rid of the water. THF has a decent amount of water in it. And then you start distilling the THF over, leaving the stuff behind. But when you get to the very bottom, when it's almost evaporated, what you've got left is explosive. And Caltech lost a building, is what I've been, no, not a building, they lost an entire floor. They lost an entire floor because someone was distilling THF this way, and it blew up. And they were distilling a lot of THF, meaning that once it got close to the end point, they had a lot of leftover material. There's just a lot of junk in there. And it just happens to be THF's reactivity tends to make epoxides, which are massively explosive. They have lost an entire floor. So what they've done since then, and this also came from Caltech, where what you now do is you make like fractionation columns, and you make them out of aluminum, which is very reactive with water, and molecular sieves, which also capture water. And you do this in a nitrogen environment, which gets rid of the oxygen. And you just run it down this column. It's called a Grubbs column, invented by Nobel laureate Robert Grubbs, who I think was here not too long ago, actually, giving a talk. Anyway, I prattle on and on. Now, what I want to do is think about how do I turn this, how can I turn this around? Now, let's say I want these two things in here. 0 and 0. Okay, I've got two immiscible liquids. Give me an idea on how to make a mix. What would be the first thing you try? Heat it. Of course you heat it. Sorry. Okay, remember that symbol from your synthetic chemistry? Heat. And turn it into this. There you go. Mixes under all fractions. Okay, now that gives me an idea of the phase diagram as a function of temperature. And it will be like this. And there's actually, in this case, I'm not really actually drawing two phase diagrams on top of each other, because I've actually only got one line. Before I had two lines. This is just one line. Yeah, anyway. So now, again, I've thrown this at you and said, this is a liquid-liquid immiscible phase diagram. Tell me what's what. One liquid or two liquids? One liquid. Okay. One liquid meaning that it's A and B are mixed together into one phase. I don't see one of those interfaces because it's hot. All right, that's how you know. Now, two liquids, the composition of which, well, if you can imagine, I draw a point there, I draw my lines, I drop them down, and this is the mole fraction of A of 1. 1 is rich in B, and the other liquid, like on top, is rich in A. Now, as I heat it up, that composition changes with heat, and then when I get here, okay, here's how I can try to trick you. I'll put you right here. And I'm going to say, what have you got and what's it made of? One liquid at, looks like 0.75. And again, I'll make the tick marks line up just fine. It'll be very easy. One liquid at 0.75. That's the answer. You just got to recognize that. Here's your mistake. You're going to do this. And don't write that in your notes. Do not write that in your notes right now because it's a mistake. This is the mistake you will make. You're going to say one liquid is pure A and one liquid is like 75% A. No, it's just one liquid composed of A and B. So don't make that mistake. Now, all right, so again, this is all very, 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 very easy. Now, it turns out that I've got two more of these to draw. It turns out that due to the complex nature of entropy, remember that K-L-W deal? Here on the one. You can also have this. Isn't that great? Two liquids, one liquid. I guess it depends whether delta S is positive or negative. So remember that if something mixes, and we're going to be at room temperature pressure, or constant temperature pressure, delta G matters. Delta G is delta H minus T delta S. Okay, so T works with S. So if I have a negative S, and times minus T is a positive number, which is bad. So in this case, when I mixed the two liquids, there was a loss of entropy. Right? That was bad. And heating it makes it worse. So that's why I go from the one liquid, I'm having the mixed phase, and what's the composition? It's whatever this is, it's like 0.6. All right, you don't do that. Well, there's two liquids with one is A and one is B. No, that doesn't make a lot of sense. That would never happen anyway. And as I heated it, because of the weird loss of entropy, not many liquids do that. Most liquids, when you mix them, they're going to want it. They're going to generate entropy. Some of them lose, which is rare, but it does happen. Okay, one liquid has this composition. That looks like 0.7, and this looks like 0.35 or 4 or something like that. So there you go. And I heat it further, and the two liquids become more and more pure. Whatever. You get this is one of the reasons I don't like this particular material for this class, because you also got this. This is very, very rare. Let me hijack my own figure just to get it this way. I don't have to draw the box. Okay, if it doesn't get any better, watch this. You can do both. Okay, one liquid, two liquids. I give you a point here. I give you a point here. You tell me that there's one liquid with 0.6 composition of A. You go up here, and you've got two liquids, one on top of the other. And here's the lower one, and here's the higher one. I don't know that. I'm just saying, one of them has this composition of A, and the other one has that composition of A. There you go. And if you heat it up enough again, they actually will remix. And there are, and this isn't fantasy, there are some liquid mixers that do this. Yeah, anyway, I thought I had this answer, but I don't. Okay, anyway. Look, I got 20 more of these. Might as well, right? Let's just get it done with. I'm not going to quite finish up. I'm not going to quite finish this today, unfortunately. So we'll spill over a little bit till Monday. Okay, these can get pretty complex. Let's do liquid, vapor. Yeah, if that wasn't fun enough. Now, at this point, I'm not even going to try to label this anymore. It's kind of ridiculous to even try. And so what you can do is get this. So here's my, what would this be? This would be two liquids, one liquid. But of course, if I heat a liquid up enough, it'll turn to a vapor. Now, if I'm already having problems mixing liquids, I know that this is not ideal. So I may have an AZ, I will have an azeotrope, it's virtually guaranteed. If the liquids don't mix to begin with. You can, go ahead, sorry. That really hurt. So, I throw this at you. Composition of A. I throw this at you, and I've drawn a line. I've asked you to label it. Now, I'll give you temperature, right? There's not that much temperature. I don't want you trying to memorize this stuff. And so it would start out something like this. And I say, fill it in, right? What you're going to do is say two liquids, right? Low temperature, that's normal. One liquid. Okay, this is liquid vapor, and then this is vapor. Makes sense. Now what have I done? I've drawn a point. I've drawn another point. I've drawn a third point. And I've drawn another point. And I say, points 1, 2, 3, 4. Tell me what the compositions are. Tell me what it is in the composition. Here, two liquids with these compositions. Here, one liquid with that composition. So this is why you might want to watch the video before the next test, because I know this is hard to write down in your notes. Okay, one liquid with this composition. Here, a liquid and a vapor. This is the liquid composition, and here's the vapor composition. And here, I have two vapors, right? One with this composition, and another with this composition.
No.
There you go, right. I know that maybe it's annoying if I say, what's wrong with this graph, like on the last homework.